Hello, everybody. So let's start the afternoon session. The first speaker of this session is Anatoli Polkovnikov from Boston University, and he's going to give us a pedagogical lecture on chaos and ergodicity in quantum and classical systems. So please.
All right. It's definitely my pleasure to be here. Put it a bit lower. So, and I would like to thank main organizer Arnab, who did like really most of the work. We just only helped slightly. So, yeah, today I will talk about chaos and ergodicity, and apparently I really like this quote, which goes to ancient Greece, that chaos came first and everything else after. And for us, I'll mention collaborators as we go. For us, kind of this entry to chaos started from many-body localization, but I'm going to present in reverse order. So, and then we started realizing that, at least for ourselves, then chaos, ergodicity, integrability, these are not all equivalent concept, and there is very interesting physics going on when we go from integrable to chaotic to ergodic systems and so on. So tomorrow I'll be talking about MBL, and we'll be strongly arguing that this is not an integrable phase, that this is a glass, or it's a transient phenomena. And I understand it's like a bit strange situation when in the same school conference you hear like lectures saying opposite things. But let me say from the beginning, I do believe that MBL is very interesting, as whatever it is. And I also do believe that disagreements are very healthy. So in this sense, they help us to understand better. But there will be no MBL today. So I'm going to start from the very beginning, is the way I see it, and I'm going to repeat some things which were already mentioned in several talks. But I'll try to give some angles, so I decided I won't like remove them just because they were said. And of course, I welcome like questions. So, and there is no like strict definition of chaos in general. It's usually defined as opposite of determinism. There are mathematical definitions, of course, but they're restricted to specific systems. And there is a sort of long history of, I would say, fight, which actually again highlights that fight is not bad for science, at least, between so probabilistic, statistical description of laws of nature, which we associate with chaos, and deterministic dynamics, whether there is a free will, probably many of you heard, because we can write some equations of motion. So, so in particular, like statistical mechanics, thermodynamics, like in particular second law, they say that any system, if left alone, reaches an equilibrium state, which is in a way maximally random. That's how we define entropy as a measure of randomness, right? And then we just constrain it to energy and so on. And yeah, this is a picture. Yeah, and by the way, I want to say, I kind of gave some version of these lectures before, like in Trieste, but for those who were here, at least there are significant updates compared to what was 6 months ago. So this is the picture I found. It actually says it's diffusion, but it's clearly not. But anyway, it's a picture showing how in color propagates. And there is one thing which I'm going to highlight many times in this talk, that if you think about entropy, then as time progresses, it increases. The state becomes more and more chaotic. In a sense, we have, we can less and less predict where a particular ink molecule will be. And finally, it reaches maximally chaotic state. And then if you just go to the street and ask, is it chaotic or not? No, everyone will say, of course not. This is not chaotic. So in some sense, maximal chaos leads back to determinism. Or at least to simplicity, let me say, not determinism, simplicity. So let's start like, well, now we go back to physics. I mean, in general, life is too complicated. So, and let's start from a one-dimensional motion, but chaos is not conserved. And I again apologize, I go through some very, very basic things just to put a stage. So if you have a particle in some potential, then of course energy is conserved, and then we know the momentum up to a sign uniquely as a function of a position. Like if we take a nonlinear oscillator, we can put a square root there, and we know how P depends on it. I want to highlight that we don't really need to solve any equations of motion, right? So we don't need to know dynamics. So, and then in particular, we can determine what's known as phase space portrait of this particle just from this conservation law. So we only need dynamics to figure out at which point in time where we are. But this trajectory is uniquely determined by just a conservation law. Right? So we have this one-dimensional motion on this shape. Now we can just compare different motions. So suppose we take nonlinearity to be small and just see what happens if you have harmonic motion and anharmonic motion. Well, anharmonic will be a little bit faster, and we see that the period is shorter. I guess black line is anharmonic. Well, then we can say, okay, well, let's try to do perturbation theory. And that's like analog of quantum perturbation theory for classical system, but it's the same static perturbation theory, which you want to do. It's kind of like doing rotating wave approximation. So then we can find a better frequency. We can correct, and then we get much better dynamics. So now we have like 3 lines, and 2 of them are almost indistinguishable. One is exact, one is harmonic, and one is like corrected harmonic. So, but if you wait longer, then we still lose track of dynamics. Just because period is still not exact. So we wait long enough, we don't know where the particle is. So sooner or later, we just lose this information. And of course, this epsilon can come from some noise, what we say, decoherence and so on. So what we can do? Well, as I said, so we can know, like without any dynamics, the probability, not probability, where exactly we are in this phase space trajectory. And then from this, we, for example, can compute probability of some position x. It's 1 over velocity, right? 1 over square root of E minus V. And it turns out that this probability is much more, okay, sorry, I switched. So, and then there is a simple observation that this probability, 1 over V, which you get from intuition, you just do random photographs, and then you ask how probable it is to see a particle here. Well, it's inversely proportional to velocity. If particle is fast, chance is small. If it's slow, it's big. But it turns out it's nothing but microcanonical distribution. Because if you just integrate this delta function that you are uniformly probable on the sphere, then you get exactly 1 over V of x. So we don't need any equations of motion, and we immediately see statistical mechanics just from time averaging in this simple situation. So this is called ergodicity. And moreover, these distributions are like extremely robust. So like, for example, if you use the same nonlinearity for which I showed you like strong deviations in the motion, if I compare distributions with and without nonlinearity, you don't see a difference. And again, the stability of perturbation theory is not, in quantum mechanics, is not because it's quantum, but because we deal with stationary information. It's very important. So in this sense, when we deal with I don't know, quantum circuits, it's not stationary. Perturbation theory is not stable, much less stable. Right? But it's the same as in classical systems. Okay, so now let's make system a little bit more complicated, and let's take particle in 2 dimensions, or like 2 particles in 1 dimension, but they don't talk to each other, so it's like separable potential. Then we go through the same arguments. Now we have 2 conservation laws, right? And if you have 2 conservation laws, we have a motion on a torus. I really don't know how to draw a 4-dimensional torus. So it's like a cartoon of 3-dimensional. Anyway, unless we have some special situations which you all know about, like 1 over R potential, harmonic, when frequencies are commensurate, we basically relax, generically frequencies are incommensurate, so we relax to product of delta functions. And this is already not a correct statistical ensemble, of course. And we heard about generalized Gibbs ensembles, and this is like example of this. And this is a generic situation for all integrable systems, when number of independent integrals of motion is the same as number of degrees of freedom. So, but you see now integrability is way simple because it's easy to solve dynamical equations of motion, but steady state is more complicated because we need to put more constraints. This is kind of interesting observation. So now let's make situation even more complex. So let's say that we have same two-dimensional system, still one particle, still classical, but now we have a general potential. And let's say that no continuous symmetries except, and basically only energy is conserved, as exactly as David was saying. So, and then we already see like what the troubles are with all previous arguments. So energy conservation allows us to find the magnitude of momentum at any point, but not the direction. So now we just don't have sufficient information to tell where the particle is, at least in momentum space for given position space. So we cannot really determine trajectories. So what can we do? And here there is this sort of struggle, like put it in quotes, between determinism and statistical mechanics. So there was like a famous principle of indifference, and I always mention that I heard it here. It is a joke always. I guess in India this joke is more relevant, but when you hear it in Boston or when I was born in Russia, it's kind of more funny. When someone asks a stupid person, what's the chances to see elephant outside the window? And the answer is 50%. Why? Because it's either there or not there. But this kind of highlights a principle of indifference. And amazingly, this stupid principle is actually underlies all statistical mechanics. It's basically principle of maximal entropy. So, and here it says that about this particle, so without extra knowledge, which is assign all possible probabilities, but subject to the constraint that energy is conserved, right? And this is basically how we get the statistical mechanics. And then this generalized Gibbs ensemble it's just already generalization by James to situation we have more conserved. So if you look into like textbooks, and for me it was, I first saw this argument in Landau-Lifshitz, there is actually more justification behind this principle. And roughly, so why we get statistical ensemble? And roughly the argument goes like this. So let's just start look into the trajectory and let's do time averaging of this trajectory. And then we get stationary probability distribution. And it's more or less obvious. It's very easy to prove, but it's also obvious. Yeah, I forgot to divide by t. Anyway, it's time average of this. So it's more or less obvious because if you start doing, I don't know, million of measurements, at some point distribution stops changing. Of course, motion is bounded, right? So you get something which is time independent. And it's something which is time independent. It means that it's a commute, so has vanishing Poisson bracket with the Hamiltonian, right? And basically it's a function of conserved quantities. But if we assume that the only conserved quantity is Hamiltonian, then we say it's a function of the Hamiltonian, but it can only be a delta function because I have fixed energy for a given trajectory. So we get microcanonical ensemble, and actually in some books it says it's even like a proof, quote unquote. And this, of course, agrees with this principle of maximal ignorance. So, and let's just do a numerical experiment. So let's take nonlinear oscillator with this quadratic nonlinearity. And this is what happens when nonlinearity is small. It's actually two trajectories, and just not to waste time, I'll show immediately what happens for the same system if nonlinearity is bigger. And we see like totally different behavior. Both systems are non-integrable because epsilon is non-zero. But in one of the systems, we immediately see this chaos, and then we slowly feel, at least this is the coordinate phase space is harder to plot. But if you look into the left picture, it seems like forever, at least as long as you can simulate, you have a pretty regular motion. It looks like integral. So, and the explanation, again, I will come to this. This is not actually exact explanation, but it's kind of intuitive. So, and that's what also David mentioned in his lectures. Yeah. Oh, sorry. No idea. What? Oh, this is equipotential surface. It's something you can never cross. Sorry, yeah, I didn't say it. It's equipotential surface. And you see, when you go in this direction, you just reach it. But if you go with some tangent velocity, you just cannot reach it because you have some parallel velocity. This is your bounds. So, and that's what David mentioned, that loosely speaking, you can understand left picture that you have emergent or dressed angular momentum conservation. Because we deform our potential, but we can think that we can also deform our conservation laws. And this is something I'm going to talk a lot today. So, but the situation is actually not as simple, and it goes back like to I guess another textbook example of a chaotic system. It's kicked rotor. So we just time after time turn on gravitational field in a pendulum. And this is described by a very simple system of equations, which called Chirikov standard Mach, and this is Chirikov himself, famous mathematician. So it's basically phase jumps whenever we have a kick, and momentum jumps whenever we have a kick, and phase freely moves between kicks, right, at fixed velocity. So, and then this is like a picture which probably many of you saw many times, but I want to show it again to highlight one important aspect. So this is as a function of kick strength, like a phase portrait, which is, say, quote unquote integrable here, and it becomes more and more chaotic, and here it becomes kind of almost ergodic in the sense that the system sort of populates the whole phase space. But I want to highlight that this picture really shows that chaos and ergodicity is not the same, right? So here we clearly see like it's very fragmented. We have some regular regions, some irregular regions. So we see definitely a lot of chaos here. Even here, if you look, I mean, you see some chaos here, right? So some unpredictability. So this actually highlights that in this picture of emergent conservation laws cannot be right. Because if you would really get emergent conservation law, if you would get a really operator which commutes with Hamiltonian, we wouldn't see this picture. We'll see a very regular picture, and suddenly we go here. Because there is only a single conservation law here. We cannot say that conservation laws disappear one by one. No, it's just one, right? But it basically disappears right here. Yeah, I'm pretty sure. Yes. Yes, but you see that Lyapunov exponents should really depend on where you are. It's actually something we are trying to figure out with David now for a different model, though, because you'll get very small Lyapunov exponents here and very big here. So when you are here, they will be all the same.
When you define chaos, does it matter where you are?
It's a good, I mean, yeah, if you have this simple phase space portrait, yeah, you can basically say this is chaotic trajectory, which is not. But I want to kind of move towards, many body quantum, whatever systems where it's not really clear what phase space point is. So yeah, I want to like go from these definitions to anyway, so, and there is actually a reason why ergodicity does not show right away, and mathematical reason, and this is also mentioned several times, KM theory, which basically tells us that all these regular trajectories are not destroyed immediately. So we need some threshold to get ergodicity. So, and basically, according to them, we can think about thermalization as gradual destruction of this integrable tori. So as far as I know, there is no proof or counterproof of KM theory in like thermodynamic limits. So it's basically most people are interested in this. For a very long time, people thought that Fermi-Pasta-Ulam is such an example. It's an example of the system which is non-integrable, it was known, but which is non-ergodic. But I'll show you later picture. By now, I think people converged from doing the numerical simulations. As far as I know, there is still no mathematical theory, but numerics suggest that eventually the system is ergodic. And for those who didn't see this, it's probably first beautiful example of computer experiment. Just a second. So it's a nonlinear chain of oscillators. This is original paper from this picture from Los Alamos preprint. And they prepared particles in one of the normal modes and see normal mode population. And then if it's equilibrates, you expect equipartition. But they see strong revivals, which actually last for extremely long times. Yeah.
So at least from what is quantitative, does that even most of the torus of the curve?
Yes.
And because each torus has a linear, so in that sense, they're also.
Yeah, you might be right. I don't want to say about it. But numerically, definitely chaos appears a little bit, but it could be, I guess there are experts who can tell. Is it you'll get a fraction of phase space which gets Lyapunov exponents, and then some fraction will get large Lyapunov exponents and the other will not. So yeah. I really am not expert here, so maybe someone can comment.
This is precisely the question I was trying to ask, that in your definition of chaos, is it enough to have a positive Lyapunov exponent in some part of the space, or?
I don't really want to define chaos. So, but I think, yeah, people normally will say as long as you have some Lyapunov exponent somewhere, the system is generally chaotic. But then there is hierarchy, weakly coaxing, mixing, and so on. So, there should be some mathematicians who would clarify that. I don't want to define anything. I just want to lead to how we think about it.
And what's the definition of ergodicity that you're using?
Well, again, I'll come to when we talk about many-body systems, maybe it's better to call it thermalization or mixing, but basically ETH. So we'll try to converge to this. Right. Yes, but this is sort of like a test. But in a way, ETH guarantees you there is no dependence on initial conditions. So whether you can have like other, again, I don't want to go into like mathematics of what is possible. You can, yeah, it's complicated. For small systems, I think it was studied. I'm just not expert, but for many particle systems, I don't think there are counterexamples which show like thermalization under all initial conditions and no ETH. At least I never heard about any example. So now let's go to quantum systems. And again, the story is very long and I'm not representing in historical order, but let me just try to start from like attempts which are sort of natural. And this out-of-time autocorrelation functions, which were also mentioned several times, they date back to actually Larkin and Ovchinnikov, back to '69. And then there was works by Kitaev. And I just want to highlight that this out-of-time autocorrelation function is actually equivalent to echo. And in this form, it was actually studied by Boris Fine before Kitaev, like independently. And then Markus Schmidt and Stefan Karain showed that this echo is equivalent to out-of-time autocorrelation. I'll mention what that echo in the picture. But basically the idea, and again, it was mentioned in previous talk, that we study square of the commutator, and then why it should work? Well, because in the classical limit, at least, it squares to maps to square of the Poisson bracket, and the Poisson bracket is nothing but derivative of x of t with respect to p at time equals to 0 squared, right? So it should diverge with twice the Lyapunov exponent. And then we can average over some initial state. It could be very important which initial state, but let me skip this. And anyway, so in this paper, actually 2013, Boris Fine studied echo, as I said, and it mathematically maps exactly to OTOC. And the idea was that you start from weakly magnetized states, actually very similar state to what Pedram showed. You start from this weakly magnetized state, but in a situation when magnetization is not conserved. And then you wait for some time and magnetization disappears. It's a numerical experiment. After some time, you do a tiny perturbation in your system and then propagate backwards in time. And then if your perturbation is 0, you recover magnetization completely. But if it's non-zero, it should decay in time. And then you might expect it will decay with Lyapunov exponent. And as I said, this exactly maps to O of time order correlation function, and that's 1 minus f. It's basically deviation of magnetization. And you see that it grows exponentially. And this is classical spin chain. It's already many body. It's many particle, right? And then you can, it's a way if you want to measure Lyapunov exponent when you have multi-dimensional space. Like looking into specific trajectories is very complicated. And then in the same paper, he studied a quantum chain, looked into exact same echo, and then to a big surprise, he found that it's not exponential. It's polynomial in time. So in this sense, this OTOCs could be a nice measure of classical chaos, but it doesn't capture quantum chaos, or whatever we say, quantum ergodicity. So this chain is completely ergodic. It has like, you see, ETH or random matrix level statistics, which I also mentioned. So. And then there was a proof in Tomaz Prosen group that actually if you have local bounded spectrum, then out of time order correlation functions, they cannot be, it's most polynomial. So the attempt, it's a nice attempt to sort of define chaos like this, right? You find a quantum object which is very similar to classical, and you hope that you extend definitions, right? And it fails. So there is another idea which is actually more recent. It's called operator spreading. It's also appeared in the talk, but here let me just look into this idea from a different angle. I also want to highlight how similar quantum and classical dynamics are. So I can, on the one hand, I can solve my Newton's equation for a particle in some potential. It's actually 1D, but it's the same in 2D and so on. On the other hand, I can find Heisenberg evolution of an operator in quantum mechanics. And let me do short time expansion of this. So up to second order, we all remember it from high school, not high school, middle school, right? Well, depends on where you are. So that x is equal to x naught plus, oh, I forgot m. Oh, my m is equal to 1. No, it's okay. So plus vt minus t squared over 2 times whatever acceleration, right? So now we can do the same quantum mechanically, and we find exact same expression, but it's kind of hard to compare, right? Because these are numbers, these are operators. So this is something I cannot mention, unfortunately, but I hope most of you heard that there is a Wigner function. Anyway, just to say there is a one-to-one map, and it's not unique, there are many maps, but it's one, I would say, most famous map. It's called Wigner-Weil quantization. It's a map from operators to numbers, and it's unique, it's one-to-one. So, and in this way, we can associate operators with normal phase space variables. So now, because it's unique, we can say that this is equivalent to this, but it's also equivalent to this. So we are saying up to t squared, our evolution is completely classical. Again, this is evolution of operators of functions. So our initial conditions, distributions can be quantum, but evolution itself is classical. So let's do one more order. So this is probably less familiar already, but it's there. So I do short time expansion. And if I do it in quantum mechanical way, I will get, of course, I must get a Hermitian operator. So it will be a symmetrized version of this. But now if I take Weil symbol, I'll get the same thing. I can do one more order, t power of 4. It's still the same. So at some point, you start worrying, like, where's quantum mechanics? Well, maybe at order t power of 5, you do it, no, it's still the same. Quantum and classical, I don't know, is it quantum and classical not that different? Yes, you do it carefully. You see, once you do well symbol, order doesn't matter because these are numbers. Well, you get symmetric versions of these operators in quantum mechanics. But when you take well symbol, you get exact these products. I don't know what you mean separable. So quantum mechanically, you see, quantum mechanically, this is not even a Hermitian operator, right? So p squared, but you will get something like p times v triple prime plus 2p v triple prime p plus v triple prime p divided by 4 and so on. But when you take well symbol, you'll get this. It's actually, apart from this, it's the Swigner-Weil quantization is very compact way of representing Hermitian operators. You can always undo it and get it, right? So, I mean, it's easier to write the Weil symbol here than this. And it's also very often easier to compute commutators. You just use Moyle product and so on. It's really beautiful formalism. I don't go there. So up to t power of 5, quantum mechanics and classical mechanics is the same. So you really start worrying. You go to t power 6, and finally you see it. Yeah, so they're not identical. So quantum mechanically, you find some weird correction of the order of t power 6, of course, h bar squared. It's proportional to third and fourth derivatives of v. And this is again to highlight that if you have harmonic motion, everything's all evolution is classical. And by the way, it's a student, someone is interested. That's the way to define quantum trajectories, at least at short times, and one can study them. It would be interesting what's going to change compared to classical trajectories. Okay, but now let me come back and say how it's related, possibly related to chaos, and coming back to what was already introduced, that actually what we are doing is a short-time expansion, and this is called operator spreading, right? So we basically see how initial operators or functions, I just highlighted that again, you can study it quantum mechanically, classically, it's almost the same, yes.
It's very strange that you have to go to such a high order, but
yeah.
Would that change if, if I have a canonical structure that is not dx dt equals p, but something nonlinear, like for example, if I have couple spins, yeah.
Yeah, you see, I'm waiting for a student who will do it. I did this myself. I repeated it in 2D, but I thought I will wait for someone to do it for spins. It's probably low. I was expecting T cube. I was surprised. I asked every single person, actually including Michael Berry, and everyone didn't believe me. If you say that up to order t power 6, there is no difference between these commutators and Poisson brackets, it's so unexpected.
The Moyal bracket, right? It's Poisson at order
up to,
h bar,
exactly.
And then the next correction is something
it's cubic,
else. So,
exactly. That's why I expect T cube.
So
yeah.
It's something because the Poisson brackets are very simple because you have just dx dt equals p, right? Probably.
Yeah, I mean, of course, it's probably related to the fact that I have p squared or whatever. I think it's interesting. Again, part of the reason I showed it, I think it's probably interesting to follow up. So if anyone is interested, like to answer some of the questions you asked, because and it's also coming back to operator spreading, which was studied for spins, for example, like comparing quantum and classical should be very interesting in this respect. S1/2, 1, and so on. Like, yeah, because you can, yeah, anyway, I don't want to go there. There are many interesting questions. But now we can ask like what we do mathematically, right? And mathematically we are doing expansion in so-called Liouvilleans or commutators, so you can say Poisson brackets. I keep H bar here, by the way, not want to highlight that classical limit is well defined everywhere. At some point I will drop it when I discuss quantum models. So, and then just a shortcut. probably many people heard about this or know this well, that equivalently there is like a lot of work in defining Krylov operators. These are basically orthonormalized set of this nested commutators. And anyway, there is the same information. Yeah, and then there was a very interesting, idea in the group of Ehud Altman, the paper in 2019. And the idea was, or conjecture, I would say, that if we take generic chaotic systems, and I want to say in this paper, they were super careful. They really said which systems they meant and so on. So it's really a beautiful paper. So, but they say basically they studied the spin systems. They didn't call them chaotic. They said generic, so that there are no selection rules. But basically they said that you expect that this nested commutators, this operator spreading, will be maximally fast compared with Lieb-Robinson bound. And maximally fast basically means factorial. There is some corrections in 1D. I just don't want to go into details. 1D is a bit slower, but let me ignore it. And the idea is very simple. It's like in each step, you produce more and more commutators, right? Because you spread in space. You start from operator of size 1, if you think about spin chain, then you start size 2, then size 3, and so on. So each time you get extra factor of k coming from the spreading. And I just want to say the same idea works if you take, say, classical spins or say this particle in the potential, then we have spreading in terms of polynomials. Each time we compute Poisson bracket, we increase degree of a polynomial spins, right? We go from a single spin to 2 spins, 3 spin, and so on. So the same kind of argument holds. So, and they had this conjecture so that basically this short time expansion knows how the system is chaotic, which again makes sense. So chaotic or whatever, ergodic, generic systems, they should spread fast, but integrable systems, they have too many cancellations, too many conservation laws, and they cannot spread. And we also heard this in the talk. And it's interesting that actually this conjecture was confirmed again before it was formulated by the work of Boris Fine separately, same year, well, next year, 2014. They studied high frequency tail of correlation functions. They didn't relate it, of course, to operator spreading, but they noticed that in integrable spin chains, this tail decays faster. And maybe I'll mention at the end why this tail is related to operator spreading. But basically, the result was that in integrable, I think XXZ chain, the operators were spreading slower. And then there was much more refined paper by Lev, who is here, and Marcos, and they also found the same result. However, so one can say, well, maybe we can try to use this as a definition of chaos. But now this fails in opposite limit in classical, and maybe I'll mention it there. So basically, if you take even a particle in nonlinear potential, one-dimensional particle, you will see this factorial spreading, basically. So this approach also doesn't work. The story is not over, but at least these are all known to me attempts to define quantum chaos based on some kind of short time expansion. So Lyapunov exponents tell us about short times, and then you do like Taylor expansion and so on. It's interesting that one conjecture works well in classical limit, another works well in the quantum thermodynamic limit, but they don't match. So what do we do? Well, let's give up on chaos. Let's look into ergodicity and thermalization. And this was mentioned in some level of detail already. I'll just go briefly through this argument. But again, I want to highlight a few points. So yeah, if we don't, as I want to say, we don't even try to, at this point, don't attempt to define chaos. We just say, let's require that our observables thermalize. This is ergodicity, mixing, thermalization, like find your favorite word. And then our wave function evolution is simple, right? So if you look into expectation value of observable, then it will be given by this sort of double sum. And then we look into time average, like David mentioned, that we look into long time limit almost at all times, but these are like simple generalizations of this. You look into average, the first square, then average, then and compare with time average squared and so on. Anyway, there are some subtleties, but basically the idea is that if we just look into time average, we see only that probabilities to occupy energy eigenstates survive, and these probabilities don't change in time. So it means that thermalization, if the system thermalizes, right, it must be built in the structure of eigenstates. And then we should see it through observables. And I would say it was realized very early on, and then there was like well, real breakthrough coming from Deutsch and Friedrich mentioned. So, and if we say that each eigenstate is roughly microcanonical ensemble, then we will see that the systems do thermalize. So let's see where this conjecture might come from. Well, let's go back to this simple one-dimensional oscillator. And then you all know that if I look into wave functions, I'll have WKB approximation right here, and this is like oscillatory wave function. I square it, I still get oscillatory pattern. And this oscillatory pattern basically modulates a microcanonical ensemble. So you see, again, like in the first classical argument I get, we recover microcanonical ensemble here from stationary states. But what if the system is non-integrable? Well, we get a nested trajectory, and then the question, what do we say about eigenstates? And for a long time, this was sort of a mystery because we kind of need to solve like very simple Laplace equations, but with complicated boundary conditions. And there was always, I think, like the idea that we just don't know how to solve it. We should try harder. And then Perry came up with conjecture, also formulated in terms of Wigner functions, but essentially what his idea, his conjecture was that these eigenstates in some billiards are just random superpositions of plane waves within given energy shell of the order of h bar. And this is like a picture also from some Wikipedia, Scholarpedia. So this is like a spatial probability distribution of state number 6000 in some billiard, and also random superposition of plane waves, and statistically they're indistinguishable. This conjecture works very well. Oh, it's as it's shown. If you ask me what's the mathematical equation, I have no idea. Well, because it looks like heart, I guess. Radiology, it's my guess. It's a nice picture. So, and then there are, shortly after, there were two powerful conjectures. One is Berry's name again of Berry and Tabar, that if we have generic non-chaotic systems or integrable systems, I should say, then they should have Poisson statistics. And if we have ergodic, well, people call them chaotic systems, I want to come back to this, then there should be random matrix statistics. Actually, conjecture should be attributed to Berry because apparently he told about this conjecture to Bohigas, but probably he didn't know how to do simulations, or didn't want to do simulations. But I think the proper name is like Berry Bohigas Jalonia-Smith conjecture. Yeah. Oh, I see. Maybe I missed it. That's mine, because mine actually, we honestly even asked this question. Of course, he realized everything, because if you formulate this Berry-Tabar conjecture, you immediately realized, but he knew about random matrices and so on. But again, my guess that it's exactly as yours. I didn't ask this question, but that's my interpretation, that probably he didn't have numerics. But yeah, he knew about this. And probably, yeah, that's why he. But yeah, it's definitely his conjecture. I mean, he came up with it. Yeah, and this is an example. So if you have just simple integrable system like a rectangular potential, and we look into level spacing statistics, then these are incommensurate sites. I forgot what they are, but there is something like golden ratio or something else involved. And then you see very beautiful Poisson statistics. And then this is original paper from Bahiga, or a picture from Bahiga's paper, and where you see QA statistics. And by now, no one really doubts this conjecture, at least in chaotic billiards. Actually, Berry even wrote that he's not sure why this is a conjecture, because in late 80s, people understood what it is. So maybe something was proved. Okay, so just to mention another manifestation of this is really a manifestation of random matrix theory, right? We get, this is the origin of Bahiga's conjecture, and the other is spectral form factor, which was mentioned in many talks. Just want to highlight that this is a measure which does not involve, I don't know, any matrix elements. It's just sort of overall measure of energies. So we just take this partition function, but with time instead of temperature, and square it, and then it shows this ramp, which is actually a characteristic of level repulsion. And there are many papers. So this is for like SYK model, but basically all ergodic models show it, and this is one of the standard tests for Ergodicity. So this is also what was introduced. So I guess, of course, Deutsch was first who formulated ETH, but I think Mark Srednicki deserves equal and probably bigger credit, because he really formulated ETH conjecture as we all know it now. So essentially, this is a generalization of random matrix theory, and because our chairman already introduced it, I will just skip. I was a bit sloppy in notations. I didn't put indices M and N here, but it's the same thing. So let me just mention one thing. So this O, as it was, it's microcanonical average. And let me just say that, well, this function f itself is meaningless because it's multiplied by some random number, but its absolute value squared is meaningful. And this absolute value squared is basically a combination of spectral functions. And they will appear later in the talk. So these are Fourier transforms or autocorrelation functions, symmetric and anti-symmetric of temperature. And temperature appears through density of states, as in statistical mechanics. I want to highlight there is no Gibbs distribution here. So if temperature is infinite, so we are in the middle of the spectrum, maximum density of states, then F is just symmetric correlation function. And then without going into details, I just want to say that from this ETH ansatz, we just recover fluctuation, dissipation relations, and Sage relations, and so on. So in a way, this is like a very nice mathematical formulation from which we can recover all thermodynamic laws without any other assumptions. Okay, so let me, this is like was my sort of introductory part. Let me finish by sort of this philosophical remark related to the beginning of my talk. So we see most systems are like chaotic and most systems are ergodic. And then we just look into another textbook example. We have a piston and a gas. And actually, we use this example to highlight that we have, I don't know, some Newtonian dynamics for this piston, right? So we just say that there is extra force coming from pressure, maybe a little bit of friction, but essentially we have Newtonian dynamics. And this is kind of an interesting point to stress. So this system is like as chaotic as it can be, right? It contains not one particle, but many particles. And yet we write deterministic equations. So actually from chaos, we go back to determinism. And this actually is sort of interesting point, which I want to stress. It may be obvious, but it's not completely obvious, let's say. Not everything is obvious, let me say so. So at least we know chaos leads to thermalization and it leads to equal probabilities. And because we deal with large numbers, we can apply, loosely speaking, central limit theorem, and then observables like pressure, whatever, they don't fluctuate. And because they don't fluctuate, some macroscopic motions, like large objects, they become deterministic. And then we don't really need to solve any equations of motion to understand what piston is doing. So we kind of go from chaos to determinism. And we can extend it further. And if you think about this, like friction, viscosity, pressure, electromagneticness, elastic response, sound propagation, actually, you can even show that mass, inertia, and so on, they all come from determinism. We are actually working right now on saying that maximal minimal action principle is actually also coming from maximal entropy principle. Chaos kind of leads to probabilistic determinism, and processes develop along Planck's probable direction. And just to highlight that this trivial point is non-trivial, and this is sort of an exercise, especially to students, to think about. Because of this thing, there is no issue of an error of time. Because very often we hear, oh, kinetic equations, they violate our Newton equations, though are kind of reversible, and kinetic equations are non-reversible. There is no really paradox here. It just comes from, if you go through the steps, you'll see that there is no paradox. So it's sort of like a concept of dualism between chaos and determinism. So we can say that determinism, which is encoded in this unique solutions of equations of motion, it leads to chaos. But chaos actually leads to statistical mechanics and so on, and back leads to determinism through this large numbers, central limit theorem, and so on. So if you want to ask who is the winner, I would say no one. Equally right. It's actually really interesting. Look, all physics laws are actually like a circle. You know, like you probably saw in statistical mechanics, Gibbs follows from microcanonical, microcanonical follows from Gibbs. And actually here, microscopic laws of nature follow from statistical mechanics, and statistical mechanics follows from microscopic laws of nature. Okay, so now I'm sort of done with introduction. And I'll go to new stuff, which are more related to my own work. So I just want to highlight this very DGS, ETH, RMT. They are measures of ergodicity, thermalization, mixing. I don't want to define even terminology for the reasons like people ask me hard questions. What do I mean by this? Maybe thermalization would be like the best word, but not chaos. So like these conjectures are inconsistent with KM. Like for example, yeah, before I go to example, I actually wrote to Barry just to make sure I don't say something completely stupid. And this is a literally quote from his email. I hope you don't quote me as defining quantum chaos. I never did. Instead, I responding to the no quantum chaos people, I defined quantum chaology. And then there's like references to the papers. And actually, again, if you didn't read them, I would highly recommend. One of them is quantum chaology, not quantum chaos. He had somewhat different views that I'm going to present, but he was like really strongly opposing like even the notion of quantum chaos close to the classical input, because for him, chaos was always classical limit, and this limit is singular. Basically, this is roughly the argument in his. But now, sort of going back to this, we can take, I actually was playing with this example myself. I prepared when I was teaching quantum mechanics, and I showed I will use it in particular to show like random matrix statistics. Of course, there are some symmetries, you just break them and so on. And there are no traces of random matrix. I spent a lot of time, but okay, maybe I didn't try enough. But then I mentioned some mathematical physicists from UK, and actually independently, he told me that many people try to reproduce random matrix statistics and soft potentials, and they failed. So again, I'm not expert in this field. I don't really know what are the conditions, but I'll show you another example, which is clearly chaotic, which shows no traces of random matrix statistics. So if we take, I would say, random matrix statistics, so HH's definition of chaos, then we are forced to say that this is a not chaotic system. This is period. I want to say it's important. So like many people, including myself, by the way, were saying that this level statistics is a signature of quantum chaos, is definition of quantum chaos, and so on. We face a big problem. So level statistics is more than chaos. Yes, most likely. I didn't check it, but almost certainly it's not ergodic. Yeah. So it's yeah, and actually there was a lot of confusion, including, I would say, MBL literature, which I'll try to mention tomorrow, by mixing like chaos, ergodicity, and integrability. This is a really different concept, and you don't go from one to another easily, even when you deal with many-body systems. So, and this is another picture I found. Actually, I never thought I will quote something from Teach Me Physiology. But when I was looking at a picture like this, I was just too lazy to draw it. Actually, this is the best picture I found. So this is again to highlight that strong integrability breaking is not what we call ordinary largest chaos, strongest chaos. Because if we have strong interactions, we have, say, big viscosity, we have like laminar flows. It's sort of like fast thermalization. We can write, I know, some diffusion equation, hydrodynamics, which are sufficiently simple. And if our systems are almost integrable, have large Reynolds number, small viscosity, we have like crazy motion, right? So systems, it just tells you that when you go, like forgetting all details, quantum classical, it just tells you when you go from integrable to ergodic, you actually go through something extremely complicated. You don't go right away from one to another. So, and then this is like also another nice example of sort of the same thing. So we just see that before we see diffusion, we have so complicated dynamics. So this is obviously more chaotic than sort of late time dynamics when we have uniform blob, right? And this is, it's neither thermal nor integrable, right? So there is no local temperature. We get some complicated turbulent cascades and so on. I mean, yes, people use name of pre-thermalization, but maybe you can say it's some kind of generalized Gibson sum, I don't know, but it's clearly something very complicated, right? So if you want to think what chaos is, we of course have some highly unpredictable, unstable dynamics, but not necessarily trajectories. These are like large objects, right? In these pictures, well, we don't know what trajectory is, right? We just look into the whole thing. We actually have emergent long time scales, and this will be like one of these highlights of what I'm going to present. Then chaotic systems, yes, they're unstable in short times, but they all have also non-trivial long time dynamics. And these things come together. So we can have large inhomogeneities, and then of course, at the end, we can have ergodicity. So I'm not contradicting myself. I'm not saying that chaos doesn't lead to ergodicity. I'm saying it doesn't necessarily lead to ergodicity, or might lead to ergodicity at extremely long times. So we see chaos just before we see ergodicity. Or it's some turbulent flow, I don't know, some flame. I have no idea, actually. I think it's some jet stream. I was searching for turbulence. So this picture illustrates turbulence. Yes. Then also will we have such a situation that there is no random? I'll come to that. Yeah. Well, this is MBL. It's chaos without random matrix theory. I'll come to that. And not only, you don't need disorder. It's just, it's very, very generic situation. Okay, so anyway, so this, yeah, and now I'm coming back to our work. It was led by Mahit Pandya and Dries Sells. It was, I would say, pre-MBL paper. And we thought an idea, okay, it was one of the ideas like how we can define chaos as some kind of instability. And again, classically, we have trajectories, so we can define Lyapunov exponents and so on. And quantum mechanically, what that time we thought of, we have eigenstates. So how about we try to see instability of eigenstates? It seems I'm again contradicting myself because I'm trying to talk about something, I don't know, not necessarily even quantum and big, and I talk about objects which are microscopic and quantum. But actually, this idea led to other developments, which I'm going to go over. So I'll spend now some time introducing what I mean by eigenstate sensitivity. So I'll try to be like, to show some equations just to show relations between different things, which will become important and important for intuition. It probably will be a bit fast if you see it for the first time, but then you can, catch up. So, but still, I'll show some equations to really highlight the key points. So let's imagine that I have now sort of a family of Hamiltonians, which are characterized by some parameter, right? And I want to deform a Hamiltonian, and I want to see how eigenstates change. So it's basically like in this previous picture, I ask how my eigenstates change if I deform my cavity a little, right? So I can introduce derivative. So I assume that my parameter is continuous. So, and I can introduce derivative of my wave function, and then it's very easy to see it's given by Hermitian operator acting on this wave function. So basically, this is an operator which matrix elements up to this IH bar matrix elements of derivative of psi lambda between n and m. So it has a matrix, and then it's one line calculation to see it's a Hermitian. So, and this object is adiabatic gauge potential. It's generator of adiabatic transformations. And then if we assume there are no degeneracies, which is not that important here, but let me do it, then I can use first order perturbation theory, right? So this deformation is like I add some small perturbation to Hamiltonian, right? I call it d lambda h. So it's like I'm saying Hamiltonian goes to h plus delta lambda times d lambda h, right? So this is like a source term for d lambda h. And then I have matrix element of Hamiltonian divided by energy denominator and multiplied by IH bar because I have IH bar in my definition. Alternatively, you can say that I have some unitary matrix which rotates my states, and this A is just given by sort of this derivative of the unitary matrix. And it appears actually in many contexts. So it's kind of very easy to see that if I multiply both sides by am minus an, that what I will get is commutator of a and h. And I see that basically this, if I add d lambda h plus commutator, I will get 0. But if you're more careful, you won't get 0. You'll get something which commutes with h. You'll get 0 up to diagonal terms. Right? So there is like first, interesting observation. So yeah, adiabatic gauge potentials, basically it's Hamiltonian, which adiabatically transforms you. So like, for example, if you do translations, this is momentum. If I do rotations, it's angular momentum. But it's generally, it's always a Hamiltonian, which moves you, smoothly moves you between eigenstates of deformed Hamiltonian. So it defines like Schrieffer-Wolff transformations, which were mentioned, and actually Floquet Hamiltonians, you can understand this way. Maybe Marine will talk about this tomorrow, maybe not, but at least he has a work about this. It's kind of interesting that this statement means that adiabatic transformations, if they exist, they associate with conservation laws. And this is actually a kind of extension of Noether's theorem. The Noether's theorem tells you that symmetries are associated with conservation laws. And symmetries are particular adiabatic transformations which don't change Hamiltonian. But any adiabatic transformation is associated with conservation law. And this kind of already hints that adiabatic transformations are related to integrability and conversely are related to chaos. Well, let me go back to classical systems. So classically, you can define generators of canonical transformations. So well, usually you see it with the Hamiltonian and time, but you can have any continuous variable. And if you have any function A of Q and P such that dx d lambda is minus dA dP and dP d lambda is dA dQ, then of course you preserve canonical relations, you preserve Poisson brackets. So this is a generator of canonical transformations. And for example, you just see that immediately P is generator of translations, right? So if my A is P, then dx d lambda is -1, it means x goes to x minus lambda, and dA dQ is 0, P is 0. You can also check, like in 2D, it's generator of rotations, angular momentum, and so on. So, but there are arbitrary canonical transformations. And I can ask, what are the special, which canonical transformations diagonalize my classical Hamiltonian? This is a bit less trivial, right? So I can say it's basically those, well, you can see, first of all, that this equation has a classical limit, but it also has a nice interpretation. I will say that if I deform my Hamiltonian, then this deformation will be equivalent to changing my canonical variables up to some diagonal terms, up to energy shifts, if you want. So, this A in this way satisfies exact same equation, like classical limit, and this adiabatic canonical transformation. So A defines them. Okay. So now it's also, of course, defines measure of eigenstate sensitivity, and because it's derivative, it tells you how quickly they change. And there is an object which was also introduced in 80s, actually in 80 by Provost and Vallée, which is called quantum geometric tensor. This is also known as Fisher information. This is also known as Fidelity susceptibility. This is basically just the norm of this adiabatic gauge potential up to factors of h bar, which at the end you can set to 1. So it's basically variance of this. So in the classical limit, you can say that the same fidelity susceptibility or geometric metric tensor is nothing but the complexity of this generator of trajectory preserving canonical transformation. So how big this function is, right? So instead of computing variance of eigenstates, you use compute average of the square over some phase space distribution. So very often when we deal with spin models, we consider averages over all eigenstates. This will be trace. So this will be equivalent of averaging over all phase space. Classically, it's always often meaningless, but in some cases we can do it. So quantum mechanically we can choose a ground state. So classically we can choose microcanonical ensembles, so we can do what we want. And intuitively, we expect large chi in chaotic systems because we have like high sensitivity to perturbations. And therefore, we need to have massive canonical transformations in order to preserve basically trajectories. So I'm not going to talk about this, but this is, I think, a nice side result. There is a whole like a direction of research related to quantum annealing and so on, which is called counter-diabatic driving. And this is the idea that if you write your Schrödinger equation in a moving frame, and you can do the same in classical, so you go to adiabatic basis, which depends on time, then you will see that your coefficients in this moving frame, so you pretend that this basis is time independent. Then you get extra term in the Hamiltonian, which is precisely velocity times this adiabatic gauge potential. And the idea which came from Demer, Planck, and Rice, and independently of Berry, that if you put this term back, you can actually be adiabatic while moving arbitrarily fast. This is known as counter-diabatic driving. And there is, like, as I said, the whole area of research for state preparation, slow dissipation, quantum annealing, and so on. And it sometimes works amazingly well. And it's interesting that this object like appears in both trying to understand chaos, as I'm going to present later, and also in a way to how to fight chaos if you want to avoid dissipation and so on.
In general, if I take a Hamiltonian, this lambda need not be a single parameter, right?
Yeah, exactly.
And then to have this chi lambda, we're going to do the same thing that one does in gravity.
Yeah, you have the full geometric tensor, and then you can diagonalize it, and you can find maximum, minimum. It's actually, I'm not going to mention about this, but we looked into this near integrability, and you have like very interesting structures. So you can also characterize like phases, phase transitions through this geometric tensor. You have directions parallel, orthogonal. So there is very rich structure. Okay, so now let me try to connect this to chaos, and I'll try for now I will use ETH or random matrix theory. Let me try to explain why this is a good measure of chaos. So I already mentioned that it's given by basically the ratio of the matrix element and energy denominator. So if we square it and sum over all states, m not equal to n, this is really what chi is, right? Variance. So I will get, I will get the sum, and now I can use ETH, which tells us my typical of diagonal matrix elements squared e to the minus s, and they're roughly all the same after the smooth function f of omega. And energy denominator is like e to the minus s squared. And I immediately see that this whole thing diverges as e power s. So basically, this sort of justifies this intuition. If my system is ergodic, I have extremely big sensitivity to eigenstate deformation. So in this sense, yes.
Yeah, so for a Fouquet system, what would be the denominator?
You have e to the I theta m minus e to the I theta m. It goes in the same way, it works in the same way. You could define sensitivity of Fouquet states.
You want to use the quasi-energies there?
Exponents of quasi-energies. No. It works. If you define derivatives, you'll get e to the I theta m. It's modular to pi, right? You put not energies, but exponents of energies. And so when theta m is close to theta n modular to pi, you'll get this, and you'll get absolute value. But the meaning is exactly the same. It's derivative of Fouquet eigenstates, right? It works in the same way. So we see that fidelity susceptibility for this ergodic systems e power s, and we know that entropy diverges either in thermodynamic limit or in classical limit. So we basically see that if we have ergodic systems, classical or thermodynamic, indeed we have something which is in. On the other hand, if you have free models, like fermions, transfer field Ising model, then this is extensive operator. Again, if you have extensive model, it's extensive operator. And it's very easy to see that this is like a polynomial function, say linear in the system size. So in this sense, we see that this fidelity susceptibility distinguishes very well simple models and ergodic models, simple integrable models. If you go to more complicated integrable models, I don't think there is a general proof, at least I didn't hear it, but in all examples we looked at, you get also polynomial divergence of chi, not exponential. And I'll try to justify it with classical intuition. Yes. Yeah, I'll come to that. Yes. Yeah, you are jumping ahead. I'm getting there. Again, I don't want to use, let me say, it's a sensible way to define chaos, but I don't want to insist too much on but let me get there, yes. So far, I just want to highlight, let's look into ETH. So I'm slowly going I'm going to answer your questions. So, and this was our initial numerical test, and it worked really beautifully. So we look into this fidelity susceptibility. We divide it by system size to remove like trivial extensivity. And we see that if we take this non-integrable Ising model, which people discussed many times, no disorder here, nothing, we see that fidelity susceptibility exponentially increases with system size, and the slope is exactly log 2. So exactly as we expect. ETH works. We see this model in this sense is chaotic. Our eigenstates are extremely sensitive. When we have this Ising model, there is even an analytic result. It's a constant. There are some boundary terms like 1 over L, which we also know analytically. And if you take XXZ model, it's actually, it looks like a polynomial on log scale. If you have linear scale, it's really polynomial. Power is close to 2, but because we don't really have analytic derivation, we don't know if it's exactly 2 or it's close to 2. We don't really know. Like numerically, this power depends a little bit on anisotropy. Anyway, so it works very well. Oh, okay. So, yeah, I have 5 minutes to go. Yeah, I think it's a good point. I'll start from really new material tomorrow. So let me just mention one more general response, and then probably, hopefully, we'll be done with this boring part today. So I want to, before I continue answering your questions, I want to make another connection of adiabatic transformations in dynamics. And that's very important. And again, I'm going to use exact same expression which I showed you, but now I want to massage it in a different way. I know I can trade in energy denominator by time and right? So what I'm going to say is that this is completely equivalent to this. I need to take principal value. Because I need to take principal value, I just need to put sine t here, right? I put mu, which is small cutoff. And in principle, I need to send mu to 0, but I will keep it as a cutoff. Because I mentioned already in the classical limit, this diverges. So I don't want to deal with infinity. So I want to look how it diverges to basically try to distinguish chaos, ergodicity, and so on. So again, you just see in this form, it's actually a classical object because this is a Heisenberg operator, which has a classical analog. And actually in this form, this diabatic gauge potential appeared in the paper of Yersinski, who showed that there is no Berry phase for classical trajectories. Anyway, then we can ask, what is the conserved quantity associated with A? And that's actually very interesting. I mean, we saw it, we were a bit surprised. It was just time average of your operator. And this is, if you want, this is really definition of L bit, which David was using, everyone else was using. And this was also used like by Tomaz Prosen and collaborators to identify some missing integrals of motion XXZ chain. For those who know, there was like long controversy between GG ensemble and so on. But it's more or less clear, if you take some operator in the Heisenberg representation time average, you'll remove all of the diagonal elements, you get conserved operator. And that's exactly the operator which appears in this definition of A. So if we now connect dots together, we see that adiabatic transformations, conservation laws, sensitivity of eigenstates, long time response, and ETH are all related to each other. So yeah, this is the last equation I want to show. So now if you want to look into chi, what we see from also the same expression, right? I just told you off-diagonal matrix elements basically related to the spectral function. And so what we see is that this sensitivity to eigenstate is essentially given by this symmetric spectral function, which determines dissipation, FGR rate, and so on, symmetric anti-correlation function divided by omega squared. But because we introduced the cutoff mu, we regularized it. So this punchline of this, that this, when we talk about adiabatic transformations, we actually talk about long time response. You might say it's obvious, but I just want to highlight it's not long time response without any deformations, right? It's response of my operator d lambda h at fixed Hamiltonian. So if I study response, low frequency response of my x, I know how this system will deform if I add x to my Hamiltonian. Okay, I think this is a good point where I stop.
Okay,
Thank you,
for
everyone.
the exciting lecture. So questions?
Yeah, I had a very simple question. In deformations of this Hamiltonian, how local can you be to see all these things, or it cannot be local at all?
Well, usually it's local, it's physical. So you just apply it on an electric field or potential. You can probe singles. You see, it's actual language which in high energy people like to use. You introduce sources to any terms you like, right? So, and usually you think about physical operators. Here I highlight d lambda h because I want to have connection between observable and deformation of the Hamiltonian. So essentially I'm just saying that if you study, you can reverse what I said. Suppose you study response autocorrelation function of given observable. And then by doing this, you actually learn what will happen to your eigenstates or classically trajectories if you add infinitesimal term to this Hamiltonian. And this could be any physical observable you like. It's usually very local, but you are free to choose non-local observables.
Thank you.
Is there any relation with spectral contraction?
Not that I know, but of course, if you assume ETH, there are like many things become related because you assume matrix elements are similar and so on. But in general, no, because this thing knows about matrix elements. This knows. A spectral form factor only knows about energies. So, but there is definitely a relation, let me put it this way, because when spectral form factor shows ramp, phi of omega is a constant. This is a manifestation of random matrix theory. So this always come together to my knowledge. So there must be some relation. But
the critical point where it starts maybe different?
No, it's tau-less time. In the systems, no. This I will highlight. So there is definitely relations of random matrix theory and tau-less time, which we define through diffusion and so on. So as far as I know, there is no like proof, at least when I spoke to Tomaz, we were saying he was defining always tau-less time through this ramp. And for us, it was always through this, and we were kind of fighting, but which is better. But at the end, it's always the same number, at least whenever you see emergence of random matrix theory, it's the same number. And I'll give some wordy justifications for this, but I don't have any mathematical argument. So there are many. I mean, one of my goals is to highlight there are actually many interesting open questions, so which like the one you asked.
In the XXZ chain, if one were to add an integrability breaking term, can one see the approximate integrals of motion, because the integrals of motion become approximate in the transformation? How does that show? It's
highly non-trivial. I will discuss this next time. So I'll spend some time on this, but you will see that it's highly non-trivial. You still get, of course, you have non-trivial approximate integrals of motion, but at the same time, you have like super long relaxation times. So you'll get huge response, exactly as you said. You expect very huge, I mean, yeah, I'll talk about this, but this is what the essence of pre-thermalization. You see, you have new time scales, which are extremely slow, which you need to basically destroy these integrals of motion. And naively, you'll think, oh, this is integrability, but I'm trying to kind of, with all these pictures and so on, to know this is actually chaos. If you have, you see, this is a very important equation, like mathematically. Physically, you have to appreciate, it takes time. It just tells you, if you buy that chi tells you about sensitivity of eigens, or sensitivity of long time trajectories, basically complexity of canonical transformation, has something to do with chaos, you just see immediately that if you have long time response, system has to be highly unstable in this sense. Again, you might not call it chaos, but I don't think you should call it integrability.
Question would be like, what are the changes to the actual integrals of, are they order one changes or their order L changes?
No, they're huge. So the integrals don't exist.
Yeah.
But so integrals are destroyed, but you have large conserved part. And this one doesn't contradict another. So it's like if you look into picture of kicked rotor. So if you try to find an operator which is conserved, forget about it, it doesn't exist. But if you find approximate operator, which is almost good, that's fine. So this operator will not commute with Hamiltonian, will almost commute with Hamiltonian. And this I will sort of discuss. But what's the fate of this operator is like very complicated and separate question. Like KM tells us that in at least finite dimensional systems, this operator will not normalize. It's approximate, but it will not normalize. So it will just, it's sort of like if you think about Earth, I mean, it's non-integrable, right? We have other planets. So there is a chaos, but it doesn't thermalize, right? So the radius of the Earth is like, but you cannot call it integral of motion because it's not a well-defined function, right? It fluctuates a little bit and so on.
A quick question.
Okay,
So you mentioned about the operator growth hypothesis and about the linear growth of the coefficients.
Yes.
And they also make statements about exponential tails in spectral function and so on.
Yes,
So
it's equivalent.
Yeah, can you make some contact here with what you have?
I don't know if I can have 1 minute, I can try to do it. Basically, if you look into this nested commutator, suppose I have L power K, I'll call V instead of d lambda H. So if you look into matrix elements of squares of these guys, so, and matrix element in the basis of Hamiltonian, which defines Liouvillean, right? This is nothing but En minus Em power K times NVM, right? So if I look into square of this, I will get power 2K. But now I want to look into norms. So I want to sum over M, say N L power K V M squared, right? So now you go through all the steps. So this off-diagonal matrix elements, they determine the spectral function, symmetric spectral function the same way. And this is nothing but omega power 2K. And for this, you don't really need ETH. It's really exact. So it's omega power 2K, then you have this phi of omega, d omega. And since you asked me, there is actually extremely interesting long short-time correspondence which appears everywhere, like I mentioned, like in chaos. If you have Lyapunov exponents, you have long tails. You know it from turbulence, from all the physics. Here, this chi, which I wrote, is essentially phi of omega divided by omega squared. So you just see that this is just minus second moment. So somehow this knows about long times, this knows about short times at large k. But they're definitely not independent from each other. But what's the relation between them is an open question. I know people tried, we tried, it's definitely non-trivial. So it's not that this leading coefficient in growth tells you about this. No, information is hidden, but it's definitely there because we know when this thing does something, this also does something. Like in this example, when this has, yeah, for example, exponential tail is factorial growth because it is a gamma function, right? So when you have exponential tail, this is constant at small frequencies. At least for spin systems, it works. Why? No one knows, as far as I know.
Okay, so and for classical systems, I guess you agree that chaos is well defined, right? Just in terms of positively Lyapunov exponent. You agree?
Yeah, but I will try to convince you that at least in the models, I'm going to discuss in some detail classical model, but we looked into other classical models. I want to argue that this is a sensible definition of chaos classically. And again, how this is related to Lyapunov exponents, I don't know. But I want to say that whenever you start developing Lyapunov exponents, you immediately start developing low frequency tail. In words, this is fragmented phase space. You have some regions with big Lyapunov exponents, some regions with small Lyapunov exponents, and so on. You have like, and this leads to long time response. But how to mathematically formulate it, we don't know. We actually, David is involved, we are trying to figure out using it with some numerics.
So you're saying even for classical systems, it's not clear how to Like
Both in quantum and in classical.
Okay.
Yeah, because in quantum systems, at least I relate it to ETH. But if you want to relate to operator growth, which seems to work for quantum spin chains, fermion models, and so on, then I still don't know how to relate it. Because I know how to relate to low frequency, long time behavior, right? But both Lyapunov exponents and short time, this operator growth is about short time expansions. And definitely short time and long time behavior, they appear in the same time. Like integrable is very distinct from chaotic, and ergodic is a very special case of chaotic. So like, for example, in terms of Lyapunov exponents, ergodic systems have narrow distribution of Lyapunov exponents. This is something which we checked already. It's just you have basically delta function. And it's clear because if you occupy the whole phase space, all Lyapunov exponents are the same. But if you are chaotic but non-ergodic, your Lyapunov exponents really depend where you start. So there is this correspondence, but how we can relate mathematically, we don't know yet. Trying to see if we can do something. It's like doing experiments and trying to make sense of them.
Okay, so time is already over. So let's thank Anatoli again.